happy to have you here and to see that the room is actually packed. Let me introduce very shortly myself. I'm the director of the Israeli Institute for Advanced Studies. And the reason that we have this event is that for the last 2 weeks or 10 days, we have quite an amazing event in Feynman building, which is our institute, in which about 130 people came from all over the world for one thing, to understand quantum, the quantum. And I'm sure that 2 weeks later, maybe there are some few open questions remains.
A few.
I tried myself to get into the hall. I must tell you, I didn't understand a thing. So I asked nicely from John to present us a talk that will be more accessible maybe to people in the faculty. So it's a great opportunity to introduce the entire faculty, mathematics, life science, chemistry, physics, all of us, to one room and to try to understand better something about the quantum. Before I give the stage to I just want to mention to those of you, Israeli among us, that wants to get a little bit of understanding what quantum is, go and read a very short story from Edgar Keller from 1992 in a booklet called Tsinorot, and it tells us something about why we don't understand the quantum. So just have to think about it. So please, Nadav.
Good afternoon. Thank you and welcome for coming to this very special and exciting lecture by Professor John Preskill. John is the Richard P. Feynman Professor of Theoretical Physics at the California Institute of Technology. He is the head and director of the Center for the Physics of Quantum Information and Matter, and is the organizer of this, along with the local committee, of this winter school. John has won many awards, among them MacArthur professorship and other famous distinctions. He is famous in the broad culture for two things. One, in the spirit of the internet, he published his lecture notes, which were an inspiration to many of us, as I remember myself as an undergrad learning from them quantum information, and then later teaching it during my academic career. And famous for the bet, along with Hawking, on the physics of information, which he might mention in his talk as well. So without further ado, John.
Thank you. Well, thank you for the very kind introduction. It's been very enjoyable and exciting to participate in the winter school here in Jerusalem over the last 10 days. I've appreciated the hospitality of the Israel Institute for Advanced Studies and the Hebrew University. It's really been a lot of fun. So this talk is going to be about quantum physics, but also, at least to some extent, about technology, quantum technology. Now, we all have technology that we use every day and that impresses us. And we recognize, of course, that the information technology we have today is going to be surpassed in the future by new technologies, which we really can't expect to imagine today. But it's kind of interesting to wonder and speculate about future information technologies. And I may not be the ideal person to engage in that type of speculation. I'm not an engineer. I'm a theoretical physicist. And maybe I'm not particularly knowledgeable about how computers work. But as a physicist, I do feel that the great intellectual achievement of the 20th century was the development of quantum theory, and it's natural to wonder how the emergence of quantum theory in the 20th century is going to impact 21st century technology. Quantum theory is an old subject by now, but there are some ways in which quantum systems and classical systems differ from one another that we've only begun to appreciate relatively recently. And those differences have much to do with the properties of information encoded in physical systems. Because to a physicist, information is something that we can encode and store in the state of some physical system, like, for example, the pages of a book. But we know that fundamentally all physical systems are really quantum systems. They're governed by quantum physics. So information is something that we can encode and store in the state of a quantum system. And physicists have recognized for a long time that information carried by quantum systems can have some intriguingly counterintuitive properties. That's why we like to talk about the weirdness of quantum theory, and we take great pleasure in that weirdness. But in recent years, we're starting to ask more seriously whether it's possible to put the weirdness to work, to exploit the unusual properties of quantum information to perform tasks that we wouldn't be able to do if this were a less weird classical world. And that desire to put the weirdness of quantum theory to work has driven the emergence of a field we call quantum information science, which gets a lot of its intellectual vitality from four main ideas: quantum cryptography, quantum entanglement, quantum computing, and quantum error correction. And my goal in the talk is to introduce you to these ideas. So let's start just by recalling that any amount of classical information can be expressed in terms of indivisible units of information. Bits, we can think of a bit as an object that can be in either one of two states, like a ball, which is either red or green. And I can store a bit inside a box if I want to, and later on I can open the box and the color ball that I put in the box will come out again, so you can recover a bit and you can read it. Now, information stored in a quantum system can also be expressed in terms of such indivisible units. Quantum bits, we like to call them qubits for short. And for many purposes, it's useful to think of a qubit as, again, a colored ball stored in a box, but where now we can open the box in more than one complementary way, say by opening door number 1 or door number 2 of the box, corresponding to different ways in which we could prepare or observe the state of our qubit. So if I store information in this box through door number 1 or door number 2, and then later on I open the same door again, what comes out of the box is exactly what we put in, so it's just as though it were a classical bit. But if we put the information in door number 1, and then later on we open the complementary door, door number 2, then what comes out of the box is actually completely random and unpredictable and has nothing to do with what we put in the box through the complementary door. So if you want to read quantum information, you have to do it the right way, or you'll damage the information. And one consequence of that can be appreciated if we think about copying quantum states. What would it mean to have a quantum copy machine? It would mean that I could put information into a qubit through door number 1 and then make a duplicate box. And then if I open door number 1 on both the original and the duplicate, the color that I put in could come out of both boxes. And likewise, if I happen to have stored information in the complementary way through door number 2, then I can open the original and the duplicate through door number 2 and find the color that I put in coming out of both boxes. But in fact, no such quantum copy machine is physically realizable. We can't, with perfect fidelity, copy unknown quantum states. And the reason is that the copy machine has to probe inside the box to copy what's inside. And if the machine doesn't know which door to open, it might open the wrong door, and that would damage the information so that we can't build a good copy. So we might be able to clone a sheep, but we can't clone a single qubit. Now, there are many possible physical realizations of qubits. I've tried to emphasize that it's useful in some cases to think about them in a more abstract way. But just so you have something concrete to think about, one way of realizing a qubit, and I'll mention some other ways later on, is we could have a single photon or particle of light. The photon has an electric field, and that electric field could be oriented either horizontally or vertically. Those would correspond to the two states if I observe through door number 1. But we could also consider rotating the polarization of our photon so the electric field is pointed along these 45-degree rotated directions, and that would correspond to door number 2. So we've already discussed one way in which quantum information is weird. We can't copy it. And that property can be exploited in quantum cryptography. So let's suppose that Alice wants to make a private call to Bob, but Alice and Bob are worried that their friend Eve is going to try to listen in. So to protect their privacy, Alice and Bob should use some kind of code. But Eve is very smart, so Alice and Bob aren't confident that they can come up with a code that Eve won't be able to break. Except they know that there's one way of encrypting communication which is really in principle unbreakable, which they can use if Alice and Bob share a random string of bits. They both have the same string of bits, and Eve doesn't know anything about it. Because in that case, Alice could take her message and she could convert it to ASCII, so it's just a string of bits. And then she could add, bit by bit, the secret string, shown in red, to obtain the encoded message, the ciphertext. And then she could send that ciphertext to Bob over a public channel. But Bob also knows the secret red string, so he can add it bitwise to the message he receives to recover the clear text and read Alice's message. Now, while the encoded message is in transit between Alice and Bob, Eve might intercept it, she might read it and copy it down, but it doesn't do her any good at all because the encoded message is completely uncorrelated with the clear text and doesn't tell her anything about it. So Alice and Bob can solve the problem of communicating securely if they have a way of generating a shared secret key, a string of random bits that Eve doesn't know anything about. But they might be in different cities. One might be in Jerusalem, the other in Los Angeles. So how are they supposed to establish that shared key and be confident that no potential eavesdropper knows what it is? That's a problem they can solve using quantum information. Because what Alice can do is she can generate some sequence of random bits, balls which are either red or green, and then she could decide at random for each one of those balls to put it in door number 1 or door number 2 of a qubit. So she can seal up the boxes and send them to Bob. Bob receives the qubits and he can decide at random for each one to open either door number 1 or door number 2 of the qubit that he receives. So that means that with probability 1/2, about half the time, Bob is going to use the same door that Alice used. And in that case, he should find exactly the bit that Alice put in the qubit. But about half the time, with probability 1/2, Bob is going to open the wrong door. And then what he finds when he observes the qubit is just going to be random junk, uncorrelated with what Alice sent. But after Bob has observed all the qubits and it's too late for Eve to tamper with them anymore, Alice can make a public announcement saying for each one of those qubits whether she used door number 1 or door number 2. And that allows Alice and Bob, through public discussion, to discard the cases in which they use different doors and keep only the cases in which they use the same doors, and now they have a random string of bits that they both share. But what about the eavesdropper? Eve might try to extract information from the qubits while they're in transit from Alice to Bob. And here's where the really special property of quantum information comes in, because Eve, if she's going to find out what's inside the boxes, is going to have to open the boxes, and she doesn't know which door to open. So if she gets some information from the qubit, she's going to disturb them in some way. And that's something that Alice and Bob can detect. They can sacrifice a portion of the key that they've generated to do a statistical test, to find out how often, when they use the same door, Bob nevertheless found something different than what Alice sent. And if that error rate is too high, it tells them that there's a danger that Eve might have been tampering with the boxes and getting some information from them. In that case, they should discard their key and not use it to encrypt a message. But in the cases where that error rate is low, then they know that Eve hasn't damaged the boxes very much, and we can make an inference that she's been able to collect only a little bit of information about the key, and then we know that there are ways of massaging the key, of distilling from it an even better key about which Eve has a negligible amount of information. So we can actually prove that this type of protocol is secure for any eavesdropping attack allowed by the laws of physics. Now this is really kind of remarkable because in most of modern cryptography, the security is based on a very different principle, that you have a code which in principle could be broken if you could solve a very hard computational problem, but we think it's just too hard a computation to be done in practice. But here the security is based on a principle of fundamental physics, that you can't extract information from a qubit without disturbing it in a way which can be detected. So this phenomenon of quantum cryptography or quantum key distribution, that's what I meant by QKD, is something that is feasible with technology today. We can send single photons, which serve as qubits, over optical fibers for distances up to about 100 kilometers, and there are even some commercial companies that are trying to market these systems. But the technology hasn't really proved its viability in the marketplace yet, and we don't really know whether there's going to be a quantum internet in our future which is used to perform such quantum protocols. The real pioneer of quantum cryptography was Stephen Wiesner, who I just saw earlier this morning. Ah, there he is. And he's sitting over here by the door. He's in the audience. And this is really his idea. And it was later developed by others. And it is now widely practiced by experimental physicists and, as I said, being offered by commercial companies for sale. But so far, we've really just scratched the surface of what's weird about quantum mechanics. To appreciate the really deep differences between quantum and classical systems, we have to consider systems of more qubits. In fact, it's enough to get started to consider 2 qubits. They could be far apart from one another. I could have one at Caltech in Pasadena and one in the custody of my friend in the Andromeda Galaxy. And it happens that some time ago, these 2 qubits were both on Earth, and at that time they were prepared in a special state which has interesting properties. Namely, I can open my box in Pasadena through either door number 1 or door number 2, and either way what I find is just a random bit which is completely unpredictable. And the same thing is true for my friend in Andromeda. He can open either door number 1 or door number 2, and either way what he finds is just a random bit. So neither one of us, by observing our qubits, can get any information. That's kind of funny because with 2 qubits we should have been able to encode 2 bits of information. That information seems to be hidden somehow. And in fact, in this case, all the information is hidden or encoded in the correlations between what happens when you open a box in Pasadena and you open a box in Andromeda. Because it turns out for this particular state, and we know because we've tested this many, many times that it's always true, that if my friend and I open the same door, we're guaranteed to see the same color. It could be red or it could be green, equal probably, but if I open door number 1 and my friend opens door number 1, we always see the same color. And also if we both open door number 2, we see the same color. So there are 4 distinct ways in which the boxes could be correlated. We could see either the same color or different colors when we both open door number 1 or we both open door number 2. And we've chosen one of those 4 ways. That's 2 bits of information encoded in the boxes. But what's remarkable and unusual is that information is completely inaccessible locally. It's entirely stored in the correlations between these distantly separated objects. And that property of quantum information, that it can be shared by distantly separated systems, is what we call quantum entanglement. And it's the really unique feature that makes quantum mechanics and quantum information different from classical information. Of course, correlations themselves are not a big deal. We encounter correlations all the time. My socks are usually the same color, and that means you can look at one of my feet and then you know for sure before you look what color sock to expect to find on my other foot. And it's kind of like that with the qubits. If I want to know what my friend is going to see when he opens door number 1 in Andromeda, I can open door number 1 in Pasadena to find out. But if I prefer to know what he's going to find if he were to open door number 2, I can open door number 2. It's almost the same thing. You might say the boxes seem to be just like the soxes, but actually the qubits are much different than classical bits. And the essential difference is there's just one way to look at a bit. But we have these 2 complementary ways to observe a qubit. And that makes the correlations more subtle and interesting than classical correlations. And this idea of quantum entanglement was first explicitly discussed by Einstein way back in 1935. And to Einstein, quantum entanglement seemed very unsettling, indicating that something is missing from our current understanding of quantum physics. And that paper elicited some interesting responses, including one from Schrödinger, who put it this way: it seems that the best possible knowledge of a whole does not necessarily indicate the best possible knowledge of its parts. What Schrödinger meant is that even if we know as much as nature will allow us to know about the state of that pair of qubits, we're still powerless to predict what will be found if I open my box through door number 1 or door number 2. And Schrödinger suggested that we use the word entangled to describe these quantum correlations. He also put it this way. He said, it's discomforting that the theory should allow a system to be steered or piloted into one or the other type of state at the experimenter's mercy in spite of his having no access to it. He meant it seems awfully peculiar that it's up to me to decide by opening door number 1 or door number 2 in Pasadena whether I will know what will happen when my friend opens door number 1 or door number 2 in Andromeda. But Schrödinger also understood that these correlations don't allow us to send a signal from Pasadena to Andromeda, because no matter what I do, my friend opening door number 1 or door number 2 is just going to see a random bit and won't get any information about what door I opened. So this idea of quantum entanglement did not develop very much for nearly 30 years until the work of John Bell in the 1960s. And with Bell, we started to think about entanglement in a somewhat different way. Not just as something weird, but as something that might be useful, enabling us to do things that we couldn't do if we didn't have the entanglement. I won't go into the details, but Bell described a game that two parties can play. Alice and Bob are playing a cooperative game. They're both trying to win. They're trying to help each other win. And the way the rules of the game work is Alice and Bob each receive inputs, and then they are supposed to produce outputs which are correlated in a way which depends on the inputs that they received. But the rules of the game are that Alice and Bob are not allowed to communicate between when they receive these inputs and when they produce their outputs. They are allowed to use correlated bits that might have been distributed to them before the game began. But for this particular game, if they play the best possible strategy, we can show that they can win the game with at best a probability of 75% if we average uniformly over the inputs they could get. But there's also a quantum version of the game where the rules are the same, except that before the game began, we distributed correlated quantum bits, entangled qubits, to Alice and Bob. With those qubits, they can play a better quantum strategy and win the game with a higher probability of success. A success probability a little bit above 85%. And experimental physicists have been playing this game for a long time, and they win with this higher probability that Bell showed is possible in a quantum world, but not possible in a classical world. So it seems these super strong quantum correlations really are part of the way nature behaves. Einstein had derided quantum entanglement. He called it spooky action at a distance. And that sounds even more derisive when you say it in German. But it doesn't really matter what Einstein thinks, because nature is the way she is revealed to be in experiments, and we should love her as she is. So the soxes and the boxes are not the same. These quantum correlations can be used to do things like win a game with a higher probability of success that we couldn't do just with classical correlations. So why is that a big deal? Is it a big deal? Yes, it really is a big deal. And we can start to appreciate why it's important if we think about systems with more parts, more than just 2 qubits. Let's say that I have a book, and it's 100 pages long, but it's a quantum book. It's a book in some highly entangled state. Well, if it were a classical book, I could read any one of the 100 pages, and I'd learn something like 1% of the content of the book, or read 10 pages and know 10% of the content. But it's different if it's a quantum book. If it's a highly entangled state of the 100 pages, then when we look at the pages one at a time, we just see random junk. It doesn't give us any information that distinguishes one highly entangled book from another, and that's because the information really isn't encoded in the individual pages in the case of an entangled book. The information is almost entirely encoded in the correlations among the pages. So if you want to read the book, if you want to tell one book from another, you have to make a collective observation on many qubits at once. If I have a relatively modest number of qubits, just a few hundred or so, and these qubits are in some typical highly entangled state, if I wanted to completely characterize all the correlations that distinguish one state of 300 qubits from another, I would actually have to write down an enormous amount of classical information. I would have to write down a number of bits which is of the order of 2 to the 300, more than the number of atoms in the visible universe. So there's no succinct way of describing all these quantum correlations using classical information. And that property was very intriguing to the physicist Richard Feynman. It led him to make the suggestion over 30 years ago that if we could just build a quantum computer which operates on qubits instead of bits, we might be able to perform tasks that wouldn't be possible with digital computers. What Feynman was thinking is that if we can't even hope to write down in terms of classical bits the state of a few hundred qubits, then maybe by processing the qubits, we could do things that we couldn't possibly emulate with ordinary digital computers. Well, back in the early 80s, when Feynman was making this suggestion, there was an undergraduate student at Caltech, where I teach, a math major named Peter Shor, and like all Caltech undergraduates, he was required to learn quantum physics as a sophomore, and I don't think he ever took a more advanced physics class than that. But like many Caltech students, he remembered his quantum mechanics and drew upon it a few years later to make a remarkable discovery. An example of a problem that we believe is hard for ordinary classical computers is finding the prime factors of large composite integers. And what Shor showed is that if we had a quantum computer, this would not be a hard problem. It would, in fact, be a problem we could solve very quickly. It's not much harder than multiplying the numbers together to find their product. So when I first heard about this discovery in 1994, I was really thunderstruck by it. I thought, this is an amazing discovery. It means the boundary between the problems that are hard and the problems that are easy, the problems that we will be able to solve with advanced technologies and ones that we'll never be able to solve, that boundary is different than it otherwise would be because this is a quantum world, not a classical world, because nature is governed by quantum physics. And I found that idea so fascinating, it led me eventually to change the direction of my own research from elementary particle physics to quantum computing. So to get an idea of how this discovery changes things, an example of a hard factoring problem today for classical computers is factoring 193 digits. Actually, somewhat harder problems have been solved now. This one was solved using a network of hundreds of workstations collaborating over the internet, and it took several months. From what we know about how that algorithm that was used to solve this problem scales with the size of the input to the problem, we can estimate that the same hardware would require longer than the age of the universe to factor a 500-digit number. So factoring 500-digit numbers isn't something that we expect to be possible with digital computers for a long time. If we had a quantum computer, which we do not yet have, but hope to have someday, which has a clock speed comparable to the clock speed of this system, can perform the same number of elementary operations per second as the classical computer, then we'd be able to solve the 193-digit factoring problem in about 1/10 of a second and the 500-digit problem in about 2 seconds. So there's a vastly different scaling of the resources that you need to solve the problem with the size of the input to the problem if we use a quantum computer instead of a classical computer. Do people care about factoring being hard? Actually, a lot of people care about that because the hardness of factoring and other similar number theoretic problems is the basis of much of the modern cryptography that we use in our everyday lives to protect our privacy. When quantum computers are widely available, we'll have to find a different way of protecting our private information. One possibility is to use quantum cryptography, as I mentioned earlier. There may be other alternatives. We don't really know for sure exactly what will be the best path to protecting our privacy in a post-quantum world where quantum computers are widely available. What was really important about Shor's discovery is that it focused attention on a new class of problems, problems which are hard for classical computers, or presumed to be hard for classical computers, but which are easy for quantum computers, which we'd be able to solve using reasonable resources if we had quantum computers. And so it becomes a compelling research agenda to get a better idea what other problems are in this class. And we've learned a lot about that in the almost 20 years since Shor's algorithm, but there's still a lot more to learn. Probably the best idea we have, which is really the idea that Feynman originally had about what to do with the quantum computer is to use it to simulate quantum systems, to study large molecules, new kinds of materials, and things like that, which we're very limited today in how well we can do such simulations with ordinary classical computers. So quantum computers would be very interesting to have. Oh, I forgot, there's a poem. So a friend of mine, Eddie Farhi, works on quantum algorithms. I wrote this poem for him. I'll just give you an excerpt from it. We're very sorry, Eddie Farhi, your algorithm's quantum. Can't run it on those mean machines until we've actually got them. And the poem goes on, but the point is that we're in a rather different position than our friends who design classical algorithms today. It's a lot of fun to come up with applications for quantum computers and to see what might be possible, but we can't yet actually run them on the machines and see how well they work. Someday, we will, I hope. So why are quantum computers so hard to build? Well, it's just really, really hard for a number of reasons. But there's an issue that might have made you worry about whether it's even possible as a matter of principle to realize large-scale quantum computers. That's the problem of errors. Quantum systems are particularly susceptible to making errors, more so than the classical digital systems that we use every day now. Physicists like to speak or imagine a quantum state of a cat, which is a superposition of the live and dead state of a cat. But we never in our everyday experience encounter such quantum superpositions of macroscopically distinguishable objects. And the reason is that we can't perfectly isolate systems from the environment, even though we try very hard in some cases. And the interactions with the environment, in effect, immediately measure a cat and project it onto either the state which is completely dead or completely alive. That's the phenomenon we call decoherence. And it's a very important phenomenon for helping us to understand why, even though the underlying laws of physics are quantum laws, in everyday experience, classical physics works very well. It's because this decoherence phenomenon works very rapidly for large systems. Quantum mechanics holds sway at microscopic scales, but when we get up to macroscopic scales, decoherence is so fast that we can't see the wonderful weirdness of quantum theory in our everyday lives. Well, a quantum computer, too, will, although we'll try hard to prevent it, interact with the environment, and that will cause the machine to make errors. So if we're going to scale up quantum computers to a large size, we're going to have to find a way to protect a quantum computer from decoherence and other sources of error. Well, we're familiar with errors being a problem in the case of classical information as well. You might have a bit which you would like to save, but there are dragons lurking everywhere who sometimes flip the values of our bits, and errors occur. We know that if we want to protect our information in the classical world, that we can do it by storing the information in a redundant fashion. So if I have this bit, which I cherish, I can store some backup copies of the bit, and a dragon might come along from time to time and flip the color of one of these balls, but I can ask a busy beaver to frequently check, and whenever the beaver sees that one color is different from the other two, he flips that color back, and so the damage can be reversed. If the dragon hasn't been able to flip two of the bits, the information is preserved because of the redundant encoding. So we would like to use the same idea that redundancy protects against error in the quantum world. Things are a little bit different, though, and it may seem challenging. We know, for example, that we can't copy unknown quantum states. So I can't just make a copy of the state of a quantum computer in case the original gets damaged. We also know that there's more than one way in which errors can occur in a quantum system. It might be that the dragon comes along and opens door number 1 of our box and changes the color of the ball and recloses the box. That would be like a bit flip that occurs in the classical world. But there's an alternative way of creating an error in which the dragon opens door number 2 and changes the color and recloses the box. That's what we call a phase error. And there's really nothing analogous to a phase error in classical systems, but we need to be able to protect against both kinds of errors to make a quantum computer work. There's another way of thinking about the phase error, which is, actually, if I open door number 1, imagine that the dragon doesn't flip the bit, but just keeps a record of the value of the bit, observes the value, and then recloses the box. That actually has the effect of changing the color of the ball when we observe it through door number 2. And because in many physical systems it's easier to record the value of a bit than to flip the bit, these phase errors are a particularly vexing problem in quantum systems. So the key thing is that if we're going to resist decoherence, we shouldn't allow any record of the state of the quantum computer to be left behind when we do our computation. If the information about how the system is being processed gets imprinted on the environment, that will cause decoherence, and that will mean our quantum computer will not succeed. We have to prevent the environment from learning about the state of the computer. We have to encrypt the computation and make sure the information doesn't leak out while we're processing the state, so that if after a quantum computation has been completed and you ask the quantum computer what it just did, it should always give the answer, if it was successful, I forget, because no record can be left behind if the quantum computer is going to succeed. So we have to find a way of concealing the information from the outside world. And we've discovered a way of doing that called quantum error correction. The idea is to store the information in a redundant way using entangled states so that the information is not locally accessible. I can take a single logical qubit that I want to protect and encode it in the state of 5 physical qubits in such a way that if the dragon comes along and makes any observation it wants on one of the 5 boxes, it doesn't learn anything about the logical state. Because the state isn't actually encoded in the individual boxes, it's entirely encoded in the correlations among the boxes, just like the 100-page book I described earlier. So this dragon can damage one of the 5 physical qubits, but that doesn't damage the underlying encoded logical information. So I can ask a beaver to check the way the qubits are correlated with one another from time to time and restore those correlations to the proper kind. And as long as the dragon has damaged only one of the qubits, the beaver will be able to reverse the damage. So again, it's the principle that redundant encoding protects against damage, but now in a more subtle form that takes advantage of the properties of quantum entanglement. Another hero of the story of quantum computing and quantum error correction is my colleague Alexei Kitaev. I first met Alexei in 1997, and it was a very exciting day for me when I heard his seminar and realized that he had an idea about quantum error correction which could be very far-reaching in its implications. The idea I heard from Kitaev is that there's a relationship between quantum error correction and topology. Mathematicians use the word topology to describe the properties of objects that remain invariant when we smoothly deform the object without tearing it. And when we think about a quantum computer which is acting in a robust way on protected information, we want the way the computer acts on the protected information to remain invariant if we deform the quantum computer by introducing some noise. So we'd like to use some kind of topologically robust physical information or physical process to do our information processing. And there is a topological interaction that physicists have known about for a long time called the Aharonov-Bohm effect, where I can imagine transporting an electron around a magnetic flux tube where the electron never penetrates inside the flux tube and so doesn't directly encounter the magnetic field, and yet its quantum state changes in a way which depends on the enclosed flux. That phenomenon is topologically robust in the sense that I can change the trajectory of the electron without changing the way this process acts on its quantum state. The only thing that matters is the winding number of the electron around the flux tube. And in fact, we know that it's at least mathematically possible to have systems of particles in a two-dimensional medium with very rich Aharonov-Bohm topological interactions. There are systems of what we call anyons, sometimes called non-abelian anyons, and they have the property that if I have many of these particles in a two-dimensional system, there are many possible quantum states which all locally look the same. The properties that distinguish one state from another are rather subtle global properties. If I look at the particles one at a time, I can't tell the difference between one state and another. So this is a kind of physical encoding of information that has just the property that we want, that the environment interacting with the system locally doesn't learn about or damage the encoded information. And also we can process the information just by performing exchanges of the particles. By having them change places, there's an Aharonov-Bohm interaction which changes the quantum state. And that means that we can imagine operating a type of topological quantum computer which we would initialize in some two-dimensional medium by creating many pairs of these anyons and then processing the information by performing a sequence of exchanges of the particles. So in 2 + 1 dimensional space-time, the world lines of these particles trace out a braid in space-time, and I could read out such a computer by bringing the particles together in pairs and observing whether they can annihilate and disappear or not. So what makes this a great idea is that the information is encoded in this highly non-local way to protect it against decoherence. If the anyons are kept far enough apart from one another, except at the very beginning and the very end, and the temperature is low enough so we don't have a lot of thermally produced anyons diffusing around, then this computer will give the right answer as long as the particles trace out the right braid. Well, at least that's the theoretical idea, and there are various proposals for how we can realize it in systems in the lab. I'll tell you about one of those. But first, I have another poem. This is in honor of Alexei, about topological quantum computing. You and your buddy were made in a pair, then wandered around braiding here, braiding there. You'll fuse back together when braiding is through. We'll bid you adieu as you vanish from view. Alexei exhibits a knack for persuading that someday we'll crunch quantum data by braiding, with quantum states hidden where no one can see, protected from damage through topology. Enyon, where do you roam? Braid for a while before you go home. And there's more to the poem than that, but you get the idea. It's a very grand and beautiful idea, but can we really realize it in a physical system? Well, Kitaev had an idea about that, which involves a remarkable trick in which you can split an electron in a physical system in half, so to speak. What he noted is that there are really two types of superconducting wires. A superconductor is something that can conduct electricity without any resistance, but there are two types of superconducting wires, the ordinary type and a more exotic type we call a topological superconductor. And if we have a segment of this topological superconductor with ordinary superconductor on either side, at these boundary points of the segment, there resides something we call a Majorana fermion. Well, what that means is that we can introduce a single electron into this segment of wire, and it sort of dissolves and disappears, can't be locally seen, but in the process, the state of this pair of Majorana fermions changes in a way which is, in principle, detectable if you brought the two Majorana fermions together. But if you look at them one at a time, you can't tell that the change has occurred. So the information has become encoded in a highly non-local way. That's a good way to protect it against decoherence. There are experiments that have been done to look for this type of effect, which have given preliminary evidence that there really are such Majorana fermions that can be realized in superconducting wires, but those experiments aren't yet definitive and may take a few years to sort things out to see whether such effects have really been seen and can be seen more convincingly. Now, once we have Majorana fermions, we can imagine braiding them, which is what we need to do to process information. We could do that in a network of wires. We can control where the Majorana fermion is, in principle, by adjusting some voltages which change the boundary location between the ordinary and topological superconductor. So if I have a network of wires, I can park a Majorana fermion around the corner, move the one on the right over to the left, and unpark the first one, and so accomplish an exchange of particles which processes the information. If I had a system of many Majorana fermions, I could perform a protected type of quantum information processing that way. That hasn't been done experimentally, but we're hopeful that it can be done in the relatively near future. Now, this is just one of many ways in which people are trying to realize quantum hardware in the laboratory. Let me quickly tell you about another one of them, which was recognized in last year's Nobel Prize, awarded to Dave Wineland. Wineland, for many years, and others, have been developing ion trap technology. They have the ability, using electromagnetic fields, to trap charged atoms, ions, for a long time. And we might imagine that each one of these ions is in one of two possible states, either the lowest lying ground state of the atom or some excited state which lives for a long time, so we can think of them as qubits. You might think it's hard to read these qubits out because they're just individual atoms, but actually it's not very hard. We can illuminate the ions with laser light, and if the frequency of that light is chosen in the right way, then one of the states, the red state, let's call it, interacts strongly with the light, and so those ions will glow visibly, and the other state, call it the green state, does not interact with the light, so it remains dark. So we can read out a series of zeros and ones in an ion trap just by shining laser light on the system. Of course, we want to be able to process the information in the ion trap to build up a quantum computation. And that could be done by taking advantage of the electrostatic interaction among the ions, which makes their vibrations in the trap coupled to one another. So I can pick out one of the ions in the trap and address it with a pulsed laser, and I choose the frequency and the duration of that pulse in such a way that nothing will happen if the ion started out in the red state. If it's in the green state, it makes a transition to the other state, the red state, and excites a vibrational mode in the trap. And then I can pick out another ion in the trap, address it with a pulse laser, choosing the frequency and duration of that pulse in the right way. Nothing will happen if the ions are not vibrating. If they are vibrating, the ion will undergo a transition to the other state, and the vibration will stop. So in other words, we can pick out two ions in the trap, and if the first one had been in the red state, nothing would have happened. If it's in the green state, then both of the ions make a transition. And so if we start out with a superposition of a red and a green state for one of the ions, we can make an entangled state. And many such operations in succession would allow us to build up a quantum computation in an ion trap. At least this cartoon is how a theorist would describe how an ion trap works. If you actually go to Dave Wineland's lab at NIST in Boulder, Colorado, things seem to be a little bit more complicated than that. There's a lot of technical complexity underlying what I just described to you, which might make you skeptical about the possibility of scaling up ion traps to very large systems. There are interesting ideas about how to do it, but there's no question that it's extremely hard technically. There are other ways of devising physical realizations of qubits which are advancing and look promising. I'll just quickly mention two of them. One is to use superconducting circuits to encode qubits, not in the way I described earlier involving Majorana fermions, but just with conventional superconductors. And although for practical reasons this isn't really a particularly good way to do it, just conceptually you can understand how a circuit can encode a qubit by imagining a loop of superconducting wire where the current is circulating either clockwise or counterclockwise. Those are the two states of the qubit. That's kind of remarkable because in this superconducting circuit there may be billions of electrons contributing to the current flow, and yet we can treat this very complicated system like it's just a single qubit encoding an elementary amount of quantum information. Another possibility is to use a single electron which has a spin or a magnetic field which can be oriented up or down corresponding to these two states of the qubit. And that encoding is also remarkable for the opposite reason. It's just a single electron, but we're able to manipulate its state pretty accurately, read it out, and get it to interact in a controlled way with other electron spins. So all of these types of hardware are extremely technically difficult to develop and improve. There's been impressive progress over the past 10 years, particularly over the past 5 years in some of these realizations, but it's still a long way to go before we'll have large-scale quantum computers that can solve really hard problems. If we ever have them, I think we will have them eventually, but there are many issues having to do with getting better materials to make the qubits better, better control systems, things that really big engineering problems in designing big systems, so it's going to take a while to get there. So I've tried to emphasize some of the different issues that come up when we think about the differences between quantum information and classical information. There are new ways of doing cryptography. There are new types of problems that we can solve with computers. There are new ways of doing error correction, which will be essential for the operation of large-scale quantum computers. And work is advancing on many fronts in devising new types of quantum hardware. But I'm really a physicist, not an engineer, so I'm especially interested in the ways in which our ideas about quantum information can potentially have an impact on other areas of physical science. And a lot of those areas of influence and impact have to do with another principle which I haven't yet emphasized concerning quantum information and how it differs from classical information. It's something we call the monogamy of entanglement. Classical correlations can be said to be polygamous. That means they can be shared many ways. So Betty and Adam can both read the same newspaper, and then they have the same information, and that means they've become correlated with one another. But Charlie can read that newspaper too, and that makes him just as correlated with Betty and with Adam as Adam and Betty are with one another, and all of us in the room can read the newspaper and join in that classical correlation. Quantum correlations aren't like that. They're hard to share. If Adam and Betty are fully entangled with one another, if they have qubits which are in the most strongly correlated possible quantum state, then Betty has exhausted all of her ability to become correlated with Adam, and she's no longer able to be correlated at all with Charlie. And likewise, if Betty becomes fully entangled with Charlie, then it's impossible for her to be correlated with the third party Adam. So this monogamy can be kind of frustrating. If Betty wants to entangle with both Adam and Charlie, then to increase her entanglement with Charlie, she has to sacrifice some of her entanglement with Adam. And that property of monogamy is the basis of many things. It's very important in cryptography, for example. We can imagine that Adam and Betty use their shared entanglement by each measuring his or her half of the state to generate a secret key. And if they are able to conduct a test that convinces them that they share very strong entanglement, then they'll know that it's impossible for a potential eavesdropper to be correlated with the key that they generate, and that's how they can ensure their privacy. This idea of monogamy is also very important in the study of quantum phases of matter and the types of phenomena that can occur in matter when quantum effects are important. Because if I have a system of many particles, like many electrons, two electrons might want to become entangled with one another to lower the energy of the system, but if electron A becomes more entangled with electron B, that will reduce the ability of electron A to become entangled with electron C. There's a type of frustration, and the system has to find the best way of relieving that frustration to find a low energy state. And different ways of relieving the frustration give rise to different patterns of entanglement. Those are the different quantum phases of matter which we're trying to classify and understand. And it's even important, this monogamy of entanglement, a subject that has received a lot of attention in the last year or two, in the context of the quantum physics of black holes. There has been puzzlement over how quantum black holes behave, how black holes process quantum information for a long time, and we thought we kind of had it sorted out. But we recently realized that the standard picture of how black holes process information really is in conflict with this idea of monogamy of entanglement, and everybody's confused, and we haven't really figured out the way of resolving that puzzle. So I've tried to emphasize that there's an area of physics which is really exciting, because this is the first time in human history that we've been able to seriously contemplate scaling up highly correlated quantum systems in a controlled way to more and more and more particles. It's a frontier of physics which in its way is just as exciting as other frontiers, like the short distance frontier in which we explore elementary particles, or the long distance frontier in which we learn about the early universe and cosmology. It's the entanglement frontier, the frontier of building up more and more complex quantum states. We think that will lead to the ability to solve problems that we can't solve with digital computers, but it's likely to lead to a number of other discoveries and insights into fundamental physics. So at Caltech, we have an Institute for Quantum Information and Matter devoted to the study of these issues. And our slogan at IQIM is "Nature is subtle." Here we are doing homage to Einstein, who famously said, "Subtle is the Lord, but malicious he is not." But Einstein really underestimated the subtlety of nature when he dismissed quantum entanglement, calling it spooky action at a distance, And nowadays, in the study of quantum information science, we have the opportunity to relish, explore, and exploit the glorious subtlety of the quantum world in all its facets and ramifications. Thanks for listening to me today. And there may be time for a couple of questions?
A few minutes.
Or just a few minutes, okay. A couple of questions. There's one in the back.
You talked a lot about dragons coming in the...
Can you say
I'm from the IIAS school down next to the university.
okay.
You talked a lot about dragons observing the quantum particles and changing the bits. How exactly can there be an observation in the bit level? How can it be changed as a single unit, not as a part of a whole unit, as you said before? I didn't quite understand that.
Well, I'm not sure I heard the last part, but so the question is about when I use the dragon metaphor to describe how qubits get damaged. The question is, how is it possible for the dragon to manipulate or cause damage to a single qubit, a single?
And you said that if the single qubit is part of a unit of many qubits, then the dragon trying to change it won't affect the single qubit.
Right. Yeah, so the metaphor of the dragon tickling just a single one of the qubits, it's based on a description of the origin of the noise in which the system that we're trying to protect interacts with the environment. You know, physicists use what we call a Hamiltonian to describe that coupling between the system and the environment. But the important thing about it is that typically the interactions are local. So there are degrees of freedom in the environment and in the system, and there are different types of environments we might want to consider. But to varying degrees, the interactions are always local. So the interactions which can cause some correlation to occur between the qubit in our system and the environment tend to act on just a single particle of the system or a single qubit in the system at a given time. A process in which many qubits are damaged is going to occur with much lower likelihood because it requires many single qubit interactions to occur together.
Okay, I'm a student here. What I want to ask is, what do you mean two doors of the same quantum particle? Let's say photon. How do you describe two doors of the same photon? What's a door?
Right, so I was a little quick with that. I did give an example of what I meant in the case of the qubit encoded in the polarization of a photon. The photon, if you like, you can think of it as an electric field which points in some direction. And we can observe that electric field, but when we make a measurement, we really get one bit of information about it. So we can learn that it's up or down, or, well, usually that's not how it works with photon polarizations. It can be either horizontal or vertical. But if I set up my observation apparatus in a different way, I'll be distinguishing between two polarization states, two directions for the electric field which are not horizontal and vertical, but are rotated relative to horizontal and vertical. Those are just two complementary ways in which we can observe the photon. But we can't do both of those measurements at once. We always have to decide to do it one way or the other.
So it's relative to your point of view.
Yeah, that's right. So you're the one who decides by choosing to make a particular type of observation whether to open one door or the other.
Let's thank again John.
Thanks. Oh, you liked it? Thank you.
Very, very much.